Hello everyone, welcome back. In this video, we'll be discussing about the last problem of yesterday's biweekly contest, number of subarrays with AND value of k. Though the problem requires segment tree to solve it fully, segment tree is just one very small part of the solution. In fact, if you look at this video, we'll be discussing segment tree in last 2 to 3 minutes of the video. Rest all is actually how to approach this problem. So if you don't know about segment tree, I would still recommend you to watch the complete video to get an understanding of how to approach the problem, and then you can learn segment tree or treat segment tree as a black box and solve the problem by yourself. So with that, let's get started. The problem states that you're given an array nums and an integer k. You have to return the number of subarrays of nums where the bitwise AND of the elements of the subarray is equals to k, right? So let's take an example. Let's say the array is 112 and k is 1. So basically you need to return number of subarrays of 112 whose bitwise AND is equals to 1, right? So there are various possible subarrays. This subarray, let's take this subarray. This subarray is a valid subarray because if you take all the elements and AND it, the value would be 1. Now let's take this subarray. Again, if you AND everything here, the value would be 1. So this is again a valid subarray. Now let's take this subarray. This subarray is not a valid subarray because if you AND everything here, you will get a 0. So we get two subarrays which are valid, which are starting from 1. Similarly, if you start from here, this is a valid subarray, this is not a valid subarray, and finally this is not a valid subarray. So among 6 subarrays, we got 3 of them are valid, and hence the answer here is 3. So hope the problem statement is clear. Now how to approach this? So brute force way to approach this problem would be very straightforward. Like you can try out every possible subarray, figure out the bitwise AND, and see if it is equals to k or not. If it is equals to k, you count it into your answer, otherwise you will not count it. So for example, you can try out this subarray. Let's say for this subarray you will figure out the bitwise AND of everything here, right? If you figure out the bitwise AND of everything here, you will see it's coming as 1, and because this is equals to 1, this is a valid subarray. Similarly, you can try out other subarrays. For example, let's say you tried out this subarray. If you do bitwise AND of everything here, it will be coming as 5, which is not equals to 1. So this subarray is not a valid subarray, so you will not increment your counter. So that way you can try out every possible subarray. There are total n square possible subarrays, right? Number of different values of L and R multiplied by you are figuring out the bitwise AND of everything here, and that can take order n time if you do it naively. So overall complexity is order n cube, right? And you can easily optimize it because you are trying out every possible subarray, and the bitwise AND of a larger subarray is simply equals to bitwise AND of previous subarray with AND of the new element, right? Because of this property, you can avoid calculating bitwise AND from scratch for every subarray and rather compute it on the fly. For example, let's say you are trying out all possible subarrays starting at this L. So you figured out the bitwise AND of this subarray. Now when you try out this subarray, instead of figuring out bitwise AND of everything here, you can say I already know the bitwise AND of everything here. I can simply AND it with this and I will get the bitwise AND of everything here, right? So instead of order n operation, you are now spending order 1 operation. So that's basically the very simple trick to optimize this order n cube to order n square, and the pseudocode would look something like this. We will try out all possible L. For each possible L, we will try out all possible R, and as and when we are trying out R, we will keep on figuring out the total bitwise and ending at R, and if it is equals to k, we will increment the answer, otherwise we will not, right? So this entire solution is order n square. Now we have to optimize this because the value of n is 10 power 5. So there are two n's here, right? One n is coming from the fact that you are iterating over all possible L, and second n is coming from the fact that you are iterating over all possible R for all possible L. So if we need to optimize this, we have to either remove this or this, and both are symmetric. Basically, if you remove this, you are saying that for each L, I want all possible R without iterating over R. Similarly, if you want to remove this, you will say for each R, I want all possible L without iterating over L. So both of them are symmetric. So let's try to remove R first. So we are saying that we will not have this loop and still want to know which all indexes this answer will be incremented at, or in other words, which all indexes the bitwise AND will be equals to k, so that we will increment the answer. Now we were doing linear search for R here. So one of the immediate thing you should thought about is can we apply binary search? If we can, then that's a simple win here, because if we apply binary search instead of order n operation, we can do order log n operation. Now two things here. When you are applying binary search, you want an array to be sorted, right? So that's the first thing we need to understand here, whether the array is sorted or not. So we'll come to that. Second thing is, we are not searching for a particular element, but we are searching for a range of elements, or all the elements where the value of AND is equals to k, right? So if the array is sorted, let's say some array is sorted and you get k here, so all the k's should be together, right? Now if you are able to do binary search, you need to first figure out the starting k and then figure out the ending k, and that way you will simply figure out how many k's are there, right? So that is our overall approach. Now for this to work, we need to first understand whether the array is sorted or not. So let's come to that part first. So what we are searching at, we are searching at the AND array, right? So we first figure out the value of AND, and then we are searching for which all values is equals to k, right? So let's try to build the AND array itself. So if you try to build the AND array for this starting at index 0, this is how it will look like. So this is basically AND of array 0, this is AND of array 0 and array 1, this is AND of array 0, array 1, array 2, this is AND of array 0, 1, 2, 3, basically this entire thing. If you AND it, it will come as 1. Similarly, if you AND this entire thing, this will come as this value, which is also 1. So we have this AND array and we are searching for 1. Now we first have to ensure that this array is sorted, and if you look at this array is indeed sorted, but the question is, it will be it is sorted for this example, but will it always be true? So I would encourage you to pause and try to think of whether it is always true or not. The answer is yes. Try to think of how, right? So let's think about it. Let's say, so what are these values? Let's talk about this value. What is this value? This value is simply bitwise AND of everything in this range. In other words, this value is equals to this value, which is bitwise AND of everything here, and with this value, right? If you AND these two things, you will get this value, right? So this value is nothing but AND of A and B, where A is equals to this and B is equals to the actual value at array of 2 itself, right? So we want to prove that this value A and B is always less than equals to A itself, right? So we know that A is on the left, and we want to understand whether A and B is less than equals to this or not. So the answer is yes, this is always true because of the property of AND. So let's assume that A looks something like this, right? We have some bit set and some bit unset. This is the binary representation of A. So some bit are set, some bit are unset. Now you are ANDing it with B. So let's say this is B, right? Here you can have some bit set and some bit unset, and then you will get some. If you AND these two things, you will get something, right? Now what will be the value at this position here? The answer is this position will always be 0. Why? Because of bitwise AND property. Bitwise AND is 0 when bitwise when you, if any of the side is 0, bitwise AND is actually 0. It is 1 only when both of the sides are 1, right? So if one of them is already 0, if the bit is already unset in A, then no matter what you do, that bit will be unset in B, in A and B as well, right? No matter what B is, right? Now, only thing that remains is the set bits. So we already know what will be the values at these bits. This will be 0, right? This will never be set. Now, only thing that remains is these set bits. Now think about it. Even if all of them are set, the final value of A and B will be equals to A, will not be greater than A any times, because whatever was unset is still unset in A and B, right? So the value will never be greater. It can be equal if everything is set, but there will be scenarios where some of these are unset as well, and in that case the bitwise AND would also lead to 0, and in that scenario it will be less than the original value A, right? So hope you got the intuition that why A is always sorry, I think I wrote it incorrectly. A is always greater than equals to A and B, right? So I hope you got this intuition. Now let's come back to the original problem that we were solving. So we wanted to understand that this array is sorted or not, and that we understood because of this property of AND. This array is always sorted, and if you look at the bitwise AND, it will always be sorted. Now let's assume that you have this array. Now what you can do, you can simply search for k and simply search for k plus 1, right? Or anything greater than k plus 1. In other words, you can do a lower bound for k and do a lower bound for k plus 1. Whatever values you get, let's say you get some L dash here and some R dash here, you can simply subtract these two to get how many k's are there, right? So what you are doing, instead of doing a linear search, you are doing two binary search, one for k, one for k plus 1. You get some values, subtract them, and you will get the total count without actually iterating over all of them, right? So that's the approach. Now, one small thing, for this to work, we need to figure out bitwise AND array as well, because we'll be doing binary search over here. So if you are doing binary search over here, you need this array as well, and this array will be different for every L. For example, let's look at this. If you see, if L is starting at 0, this is L equals 0. So if L is starting at 0, this will be the array of bitwise AND. The first one is bitwise AND of 0. Second one is bitwise AND of 0 and 1, which is this. Third one is bitwise AND of 0, 1, 2, and so on and so forth. And when L is 1, this value will completely change, because you can't really determine the bitwise AND based, you can't subtract any element from bitwise AND in a simpler fashion. So if you do calculate the bitwise AND for L equals 1, this array which you were binary searching on itself will change. So if you start your L from here, bitwise AND of this will be 5, bitwise AND of this will also be 5. Notice that these two are same and everything else is also same for L equals 1. But as soon as you go to L equals 2, everything changes. So if you see, bitwise AND of this would now become 7, whereas for the previous 2 times it was 5. Bitwise AND of this will now become 3, previous 2 times it was 1, and so on and so forth. So basically for every L, this bitwise AND array is something you need to compute as well, and computation of this bitwise AND array is not easy, or rather it's time consuming, but we will come to that. So for now our algorithm is, we wanted to reduce one n from our equation, and we were able to do it because of binary search. And binary search we are applying on bitwise AND array to do a lower bound on k and k plus 1 and subtract those to get the answer. So let's look at the pseudocode first before we look at the time complexity. So this is how our original n square algorithm was, right? So what we did, we removed this entire loop and we have figured out the bitwise, the lower bound for k and k plus 1 on the AND of L array, because as we discussed, the array would be different every time as and when L changes, right? So this lower bound function would look something like this. You have a target, you have an array, you have a starting point. Now you will simply start from your starting point and go all the way to n minus 1. You will search for the first occurrence of target, and for that, because this array is sorted in a descending fashion, the first one is the largest, the last one is the smallest. So if you figured out that okay, the value at m is greater than the target, then target is smaller, so it should be on the right side. So you will simply skip the entire thing on the left and just search on the right side, right? And if the value is less than equals to target, it means you got something, so this must be on the left side itself, right? So because at every iteration you can skip half of the array, and you can, this entire loop will simply run for order log n time, and the complexity of this entire lower bound will simply be order log n, right? Now what is the complexity for the above loop? So we have a loop which will run for order n time. Inside that we are calling this function twice, so this will be 2 log n. So let's remove 2 for simplicity. So this is n log n. But is that it? The answer is no, because notice that this AND array is also something you have to compute, and we have seen before that this AND array will be different for every L. So if you compute this naively, this will take itself order n square time, right? So we have reduced the complexity of this entire thing, but the computation of this AND array itself is still order n square, which we have to do, let's say, outside of this loop, right? So now this is fine for the given time complexity. We need to somehow remove this. In other words, we need to somehow do binary search without computing this entire array, right? And how to do it? The answer is simple. For binary search, you just need log n access of elements. So notice that you are not accessing all the elements of AND array. You are accessing only the m that you care about. In other words, you are accessing log n number of elements here, right? So the value, depending on what's the value of n, the number of elements you are accessing will differ. So if you are accessing only log n number of elements here, why do you want to compute everything here? So let's say you only want log n elements and you have some way to calculate log n elements. So you don't need to compute this entire thing, and you just need logn number of elements, and let's say you are able to compute that logn elements in logn time, like in order one time. Each of these array, you don't need order n time to compute, but rather you will need just logn time to compute, right? You need logn elements here, you need logn elements here, you need logn elements here, and so on and so forth. So basically, if you are able to compute this elements efficiently, you don't need order n square time to compute n square elements. Instead, you need order n log n multiplied by some factor, let's say x, to compute n log n elements, right? Because at the end you are accessing just n log n elements across all these array, right? Now we need to figure out x. What is x? X is the time to compute one element of this array, or like of any of these L array, n arrays. So let's think about it. Let's talk about this array itself, because this is the simplest one. So if you think about it, what is this element? Like if you want to compute this, how will you compute this? This value is equals to the bitwise and of everything from here to here, right? And can you compute bitwise and of a range efficiently? Answer is yes. You want to compute like range in a given range, you want to compute bitwise and that's where you can utilize segment tree for. And if you use segment tree, this value computing bitwise and in a range you can do in log n time. So the value of x would be log n here, and in other words, the complexity of this entire calculation would be n log square n plus n log n for this thing. So overall complexity of the algorithm is n log square n, right? So just to reiterate that last part, if you don't understand this in this way, there is one more way to understand that. Notice that you are accessing an array of m here, right? Now instead of like you can't have this array, that's sure, because to calculate this array you need order n time for each L, and you can't afford that. So instead of this, you can simply do a range query on segment tree and say, okay, I want an array of m for L. In other words, you want the bitwise and of everything between the range L and m. And when I say L, this is basically the start, not the L of this. So let's correct this part. You want bitwise and of everything between start and m, and that you can get in just log n time if you use segment tree. So this calculation of this is log n, and this calculation you are doing it inside the loop which is running log n time. So overall this entire loop will take order log square n, and this entire thing will be order n log square n, right? So that's just one other way to understand the same complexity. Basically the crux is we don't need to calculate this entire arrays because we are only accessing n log n elements. So we will compute those n log n elements only, and to compute any one element you can use segment tree to do that efficiently in just log n time, right? So hope this entire solution is clear. If you have watched to this point, I would strongly encourage you to pause and try to code this entire thing by yourself. If you don't know about segment tree, don't worry, you can treat segment tree as a black box and take the code of segment tree from the solution which I will be sharing afterwards. And I would encourage you to learn about segment tree as well. There is a complete series on segment tree in this channel itself. You can go through the videos, at least for this particular problem. If you just go through the first video, that should be enough for you to solve this entire thing by yourself, right? So next we're looking at the code. So the code is exactly what we discussed. We create a segment tree first of bitwise and, so that we can compute bitwise and in a range efficiently. After that, for each L, we are doing two binary search, first for k and then for k minus 1. Again, you can either do it for k plus 1 or k minus 1. I am doing it for k minus 1 because that will be easier. Basically, instead of this will be greater and this will be smaller, so I will just subtract these two. I think pseudo code was bit incorrect. This will be smaller than this, so this will be RL minus RR, right? But I think you get the point. So binary search solution is also, as we discussed, we will simply do a binary search starting at this particular index and going all the way till here. For each index, we will simply figure out the middle position. Sorry, for each iteration, we will simply figure out the middle position. Once we have M, we will search what is the value of AND array at L for this M. In other words, we want bitwise AND of everything between ST and M. So that we can figure out using segment tree. If it is greater than target, it means the value we are looking for is smaller, and smaller values would be on the right. So we'll simply search on the right. Otherwise, we will search on the left. And finally, this is the edge case that I was referring to here. Because we are doing a search over the existing array, there will be certain scenario where the value is not exactly within the array, right? And in that case, you need to handle those scenarios by yourself by simply adding +1 to the index you are getting afterwards, right? So that's pretty much it. Segment tree, let's look at it. It's very similar to what we have discussed a lot of times in this channel. We first build a segment tree. To build a segment tree, we'll just build the left half and the right half, and then once we have left and right half built out, it means we have the bitwise AND of everything in the left, bitwise AND of everything in the right. So we can simply bitwise AND those two values to get the bitwise AND of everything starting at current row. Now query is also straightforward. If the node current doesn't lie at all in this range, we will return some value which will not interfere with the original value. In case of sum, it used to be 0, but here we want bitwise AND, so the value will be something which has every bit set, because if anything is unset here, this will interfere with the final value as well. So that's why we put everything as set. If it would have been OR, we would have returned everything as unset, right? So this basically is the value which makes sure that nothing is interfering with, it is not interfering with the final result at all. Now finally, if the node lies completely within the range, we'll return it. And finally, if not, we will go both left and right, get the left half, get the right half answer, and then that will be our final answer. So hope this entire solution is clear. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.